Hello, welcome to a video discussing section 6.3 on properties of definite integrals. We are going to discuss the first 2 pages of these notes. So the first property we're going to talk about is the reversal of the order of integration. So as you might remember from our last lesson, if you're integrating from a to b of f of x dx, that means that you're starting here at A, you're ending here at B, you got some curve, and we're simplifying the area between the curve and the x-axis within the interval from A to B. Now, what if you put the B on the bottom and the A up top, even though B is bigger than A? When that happens, you're going to say it's negative from A to B of f of x dx. It's going to be the negative counterpart when you reverse the order. So going from left to right is considered the positive area, right to left is considered the negative area. Now, when these are the same, then you have no area being covered, so there's no area whatsoever. When those are the same, you're going to say it's 0 because you're not sweeping any area whatsoever. If you have a constant, you can pull the constant out and multiply it to the integral. And by the way, if k equals -1, then of course you put the negative off to the left. Or you could also reverse it too. Because reversing is like multiplied by -1, as we saw in property 1. And going back to the constant multiple rule again, look at the graph off to the right here. So if you multiply, if you have fx and multiply it by 2, so now it's the vertical stretch, you can see that we're doubling the area. So if this is like, A1, then what I'm doing in red would be twice A1. What if you're adding 2 integrals? Feel free to separate it, just like we did for derivatives. So AB f of x dx, and plus or minus, so same thing for subtraction. You can just break up the integral like that. Now, this one part's kind of interesting. It will play a key role in what we do in our full lesson on 6.3 next time we meet. Let's say these are the same. So the upper limit of the first integral is the lower limit of the second integral. So it's almost like you have these 2 areas that kind of link up. So you got the first area right here, and then you got the second area right here. Well, it's no different than saying the integral from A to C, just the whole thing of f of x dx. Next one's not really one we see too often, but just good to talk about. It's called the Max Min Inequality. So obviously the shaded region between the curve and the x-axis would be this. And what we're noticing is that we have a maximum y value and a minimum y value. Well, if I were to, oh, by the way, sorry, I need to shade more. Sorry about that. Gotta shade this as well. Okay. So the yellow region, and actually I'll keep in yellow for color coding. The yellow region is from A to B of f of x dx. Now we expect this, it's called an inequality property for a good reason. We expect this to happen. The maximum value of f times b minus a, or I'm going to tuck it over here, the minimum value of f times b minus a. And of course, the integrals in between. Because the thing is that if I were to do the minimum value of f, which is this right here, times the difference of b minus a, that's just going to be this area, this rectangle right there. Of course, the area between f of x and the x-axis is more than this rectangle that I'm shading in blue. Or if I take max f and b minus a, so I shade that rectangle where max f is the height and the base is b minus a, whatever that area is going to be more than integral from a to b. So a to b is going to be in between its maximum f value and its minimum f value times b minus a. Nothing we really do much with that, but just good to talk about. If f of x is always bigger than g of x, so you have this, and say g of x looks like that. So here's g, and there's there's f. The integral from a to b of f of x is obviously going to be bigger than g of x, or equals if they happen to be the same curve. And that's called dominance. So that's another property as well. So let's do a couple examples here using these properties, and then we'll end the video. So starting with example 1, let's say you're given these 3 integrals from -2 to 3 for f of x equals 10, from 3 to 7 of f of x equals -6, and from -2 to 3 of g of x, different function, equals 2. Evaluate if possible. So here, notice they're reversing this. So we're reversing the order. Sorry, I'm kind of losing my voice here. Reversing the order. So you're just going to say -2. For b, you're going from -2 or 7 to -2. Well, let's think about what's going on with f. I don't know what f looks like exactly, but let's say maybe it does something like this. That's at -2. That's at 3. That's at 7. So, excuse me. Here's the area of the first region. Here's the area of the second region. Probably should have done more of a contrast. So obviously that's 10 plus -6. And actually, from 3 to 7 should be below the x-axis, but let's not worry about that. So obviously, from -2 to 7, if I were to use the additivity property, I know the integral from -2 to 7, because this is supposed to be area 10, area of -6. From -2 to 7 of f of x dx, that's going to be 10 plus -6, or 4. That's again using the additivity property. But obviously the order is reversed here. So you're doing additivity and a reverse of the order. So in this case, it's going to be +4. Sorry, I meant to say -4, because negative this. Here, we have f of x, we have these constant multiples, so you can break it up like this. 2 integral -2, 3 f of x dx minus 5 integral -2, 3 g of x dx. Excuse me. And we know the integral from -2 to 3 is 10, so you're doing 2 times 10 minus 5 times 10. You get -30. Now for the next one, we can't do this. Even though we're doubling these limits of integration, it's not possible to determine with the information we're given. because I don't know what's going on around -4 here. I don't know what the curve is doing at -4. I don't know what's going on at 6, you know, in the middle here. I have no idea what's going on. But not possible to determine with our given info. Here we're going from 3 to 7 of f(x) plus g of x. Well, I don't know what's going on for 3 to 7 for g of x either. I know it's going from -2 to 3 of g of x, but I don't know what's going on from 3 to 7. So it's also not possible to determine with our given information. We just can't do it. And then finally for f, you're told that from -2 to 1 g of x is that, so find it from 1 to 3. So that's interesting, because I do know from -2 to 3 of g of x dx, and I know from -2 to 1 and from 1 to 3. So you can do that, that's additivity property. But it's interesting because we're given up above this right here, which we knew was 2. And from -2 to 1, we know is -1. And I gotta find what this is. Well, that's gonna be easy. That's just gonna be 3, because -1 plus 3 is 2. So that's why this answer is just gonna be 3. Because the integral from -2 to 3, the whole thing, if this were g, that's -2 and that's 3. There, the whole thing is 2. So from -2 to 1, you're told it's -1. So then from 1 to 3, that's going to be 3, because -1 plus 3 equals 2. Okay. And lastly, let's look at example 2, and then there'll be a good place to stop. You're asked to show that this is between 6 and 3 root 7. Well, what you could do is graph y equals root x plus 4. If you graph that, it looks like this. -4 is right here. Y-intercept, I think, is 2. And if I go to 3, it goes up to root 7, I believe. Root 7 is between 2 and 3. So my curve looks like this. But I'm really only interested from 0 to 3. So let me just graph that portion, because that's what my integral is like. Well, if I do this, and I do this, so I see that if I shade this part in blue, the integral from 0 to 3 of root x plus 4 dx is definitely going to be greater than that blue region, because obviously if you look at the red curve, the area between the red curve and the x-axis includes the blue region and a bit more, like this part. So, and the area of the blue region is simply going to be the base, which is 3, and the height, which is 2. So it's definitely going to be bigger than 6. And if I look at the green boundary and shade that, the area that's going to be the base, which is 3 times the height, which is root 7. But that's going to be greater than the integral, because the integral, again, is from this red boundary down to the x-axis. So the if I were to shade all this in green, that's going to be more than the integral. And so that's why I could put 3 root 7 here. And that's using the that Max Min Inequality theorem, or property, that was mentioned on the previous page, Max Min Inequality. So that's what's going on there. So again, we have some properties. There'll be a Google form to answer, and then we will do more of this stuff next time we meet. Okay, bye.